Hi everyone, welcome to the 7th lecture of E635 Applied Linear Algebra. This happens to be the third and final module. So in this lecture, we have been discussing about these two very important properties of linear maps, namely monomorphism and epimorphism. It turns out that they have different names: monic, monomorphism, one-to-one, injectivity. These are all the same things. And similarly, epimorphism, onto-ness, and surjectivity, they are all the same. Okay, and then we have seen that when a linear map is both injective and surjective, it's called bijective. And this is the situation when the map admits an inverse map. And we've seen that for a linear map, this inverse also happens to be linear. Okay. Now, we have also seen that for square maps, in the sense that for those linear maps which are from finite dimensional vector spaces to finite dimensional vector spaces, and in situations where the domain and the codomain have exactly the same dimension, in those scenarios we've seen that one-to-one being one-to-one and being onto, they're actually equivalent to each other. And then we saw that this actually translates to the fact that for square matrices, one-to-one, onto, invertible, all these three are equivalent concepts. Okay. Now, this question brings us to this next question about this invertibility business. That suppose a map is not bijective. Yeah. In that case, can we talk about inverses? Well, of course, a map could neither be injective nor surjective also. But we'll see that if a map is injective, then it will allow what is known as a left inverse. Okay, yeah, if and only if, in fact. And a map will allow a right inverse if and only if it is surjective. Yeah, that is what we'll see in this module. So let me share my screen. Okay, so this will give us the opportunity also to define this immensely important tool that is used very often in algebraic studies, namely commutative diagrams. So first we talk about this idea of left inverse. Yeah. So left inverse. Okay, so I have this V, I have this W, and I have this linear map phi from V to W. Okay, what would mean for there to exist a left inverse? Left inverse means existence of, so psi being a map from W to V is called a left inverse of phi if psi phi is equal to identity on V. Okay, so I apply phi first and then I apply psi, I should get identity, which then means something like this. So in this diagram, so I'm redrawing rather the same phi map diagram. Suppose, so I'm asking this question. Does there exist a map like this, psi, such that from V to V, there is this identity map, right? So it's the same map, like V goes to V. Does there exist a psi such that this diagram commutes? This is the symbol for commute. So this is called a commutative diagram. What does this mean? Why do we call it commutative diagram? This is so because I'm saying that start from here come here following the phi map, and then from here follow the psi map and come here. This path, or for the same element, you apply this direct identity map. If the two effects are the same as a whole, then we say that this diagram commutes. That means it doesn't matter whether you follow this path or follow this path. Yeah, so it will be called commutative diagram. So whenever such happens, it's called commutative diagram. So the question is, does there exist a psi so that this diagram commutes? That is when we say that phi admits a left inverse. Similarly, for a right inverse, the question would be, so once again, I have phi, which is a map from V to W. Psi, which is a map once again from W to V, is called a right inverse of phi if phi psi is identity on W. Commutative diagram wise, this would mean once again I have V, I have W, but I want it to be a map identity on W. So I have this phi here. Okay. Does there exist, okay, once again, red color. Does there exist a sign so that you go either this way or this way, doesn't matter. So this diagram commutes. This is identity. Does there exist a psi such that this diagram commutes? Then we say that this is a right inverse. Okay. Now, this looks like kind of a difficult question, right? How do I know whether such a map would exist or not? Matrix wise, it would mean that given a matrix, say A, left inverse means does there exist a B such that B times A is identity of some size, of some appropriate size? Or given an A, does there exist a B such that AB is identity? Yeah, how do you get that? So it appears so almost like linear equation kind of situations, right? Solvability of linear equations. What is surprising is the fact that left inverse exists if and only if the map phi is injective. And similarly, right inverse exists if and only if the map is surjective. Yeah. What we will see is that we can actually solve this existence problem without looking into matrices and things like that. Rather, if we utilize this particular idea, which we'll come to very soon, it's abstract idea, this existence question can be answered pretty easily. Yeah, and that is this profoundly important idea that we are going to discuss now. Yeah, the key. What is that key? The key is the following. Okay. So if we have a map from one vector space to another, forget about vector spaces. Suppose I have a map from one set to another. How is that map defined? I have to say where every element from that domain set is mapped to how to which elements is it mapped to in the codomain. So for every element in V here, I have to specify what phi is doing. Right? Like for example, when we say, okay, I have this function sine x. we already know what it really means. So sine x would mean that x in radians. Yeah, there's this, this the height by the hypotenuse. Yeah, for these different angles. So for each angle, it is specified what the value of sine must be, the value of the function. So for every x, what is sine x? That is what sine x really means. Although it's just a shorthand, it really means that what it is doing to every element from that set. All possible angles, how are they mapped? That is how a mapping works. When you write a polynomial function, you're saying that, okay, for every, so suppose I have this function 1 plus x squared. This means that I put this value of x, say, equal to some number alpha, then I know how to find out that number alpha squared plus alpha plus 1. So that this function, this closed form expression of the function tells us specifically what this function does to every point, right? So in this case also, when I define a map from one vector space to another, I must actually specify how V is being mapped to what vector is this vector V being mapped, right? That's what the, what should I say? That's what the common sense suggests. Yeah. However, when it comes to linear maps, you can get away with not specifying phi at all the points of this space V. Instead, if you specify what this map phi does on a basis, then you're actually done. Yeah, you don't trust me? Let's see. Suppose B, which is equal to some V1, V2, dot, 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 could be finite, could be infinite, doesn't really matter. Suppose this is a basis for V. Yeah, as a vector space over the field F. Right. Now, let V be an arbitrary vector in V. Yes, all right. I have an arbitrary vector. But because this is a basis, this means there exists alpha 1 dot 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 up to alpha n in F such that V is equal to alpha 1 V1 plus dot 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 up to alpha n Vn, right? Which then means, see, phi V must be phi acting on alpha 1 V1 plus dot 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 up to alpha n Vn, but it's a linear map, no? So this will be phi V1 plus dot 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 plus alpha n phi Vn, that's it, right? So if I know what this vector is, yeah, what these vectors are, then I know this phi V. So phi V gets specified uniquely when phi V1 dot 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 up to phi Vn are known. Yeah, which means a linear map gets uniquely specified. Okay, so its action on arbitrary vectors get automatically specified when you specify the map on the basis vectors. So let me write this down, this profound statement. Phi gets automatically and also uniquely specified if phi is specified on the vectors in a basis for the domain V. This unique part requires some discussion. Yeah. So suppose we have, so suppose phi is some map. Okay. Phi is some map and V to W such that, and V1 up to, and B equal to V1, uh, V1, V2 dot 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 a basis for V. Suppose phi V1, phi V2. Okay, suppose, let me write this down this way. Yeah, I think this would be better illustrated. So say phi V1 is equal to W1, phi V2 is equal to, let me, should I use W1? Yeah, it's okay. W2 and so on. Hmm? Suppose that there is one more map which matches on these same vectors. So let psi be another map from V to W such that uh, phi V1 is equal to psi V1 is equal to W1, phi V2 equals psi V2 equals W2, and so on. The claim is that if phi and psi are like this, that is, they match on the basis vectors, then phi and psi should match everywhere. Claim is phi v must then be equal to psi v for all v in V. That means the two maps are in fact identical, right? Why is that so? So once again, let v equal to alpha 1 v1 plus dot 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 up to alpha n vn. Any arbitrary v can be written like this linear combination because there's a basis. This would mean phi v will be equal to alpha 1 w1 plus dot 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 up to alpha n wn. But psi v must also be like that, alpha 1 w1 plus alpha n w1, right? So the two are equal. So that's why um, that's why this specifying on the basis uniquely specifies the linear map everywhere. Yeah. Great. This will be of profound consequence for us. This idea that specifying on the basis vectors uniquely specifies the map will be important for us. Okay. First application of this idea we'll see when we talk about this left inverse business, left inverse idea. Okay. So we try to prove this particular result. Proposition phi map from W, phi admits a left inverse if and only if phi is 1 to 1. I will prove only the if part, you will prove the only if part. I will prove the if part. That is, we assume phi is 1 to 1 to show that there exists psi, which is a map from W to V, such that psi phi is equal to identity on V. Okay. Now, how do we do that? Okay. We first observe the following. Because phi is 1 to 1, so for this, we will assume that, yeah, we will assume in this case that V is finite dimensional. We're going to make this assumption that V is finite dimensional. Assume that V is, although it doesn't have to be finite dimensional, but in this case, we're going to assume that it's finite dimensional. Assume that V, it makes the proof much easier. Okay. Assume that V is finite dimensional. That is, dimension of V is equal to n, which is less than infinity. Okay. So let b equal to v1 dot up to vn be a basis for basis for v. Okay. First we claim that phi v1 dot up to phi vn is linearly independent. Okay. Why is that so? Suppose not. This implies there exists alpha 1 dot up to alpha n all in f such that alpha 1 phi v1 plus dot up to alpha n phi vn must be the zero vector in W. But then phi is a linear map. This means phi acting on alpha v1 plus dot up to alpha n vn must be the zero vector. But phi is 1 to 1. This means alpha 1 v1 plus dot up to alpha n vn must belong to kernel phi. But this being 1 to 1 means it's just 0 since phi is 1 to 1. This means alpha 1 v1 plus dot up to alpha n vn is equal to 0. But then this must imply alpha 1 is equal to alpha 2 dot alpha n equal to 0. This is because v1 up to vn is linearly independent because it's a basis for v. Right? This proves that only the trivial linear combination of phi 1 up to phi v1 up to phi vn goes to 0, which means phi v1 up to phi vn is linearly independent as we have claimed. Okay, so then what we have is we are also going to assume, so that means phi v1 dot up to phi vn must be linearly independent. At this point, we make one more assumption which makes our life much easier. Assumption: dimension W is equal to M, which is fine. Yeah. So this also W is a finite dimensional vector space. So which means now, okay, span of phi v1 up to phi vn. This must be image of phi. Yeah, as we have seen before, this image of phi. This is in general a subspace of W, and this is a basis for for image of phi, right? So I have a subspace for which I have a basis. This basis can be extended to the basis of W, right? So this implies phi v1 dot up to phi vn. If it is full, then there's nothing to be done. It's already surjective, and we already know that 1 to 1 and on to together would mean that it's bijective, so inverse would exist. So left, right, both inverses would exist. But here we have only information that it's 1 to 1. It doesn't have to be on to. Right? So suppose this is not onto, which means it's not full. So there will be some more vectors. What vectors should I call them? Have I used the vector W anywhere? No, I have not used the vector W. So let me use W1 dot up to some Wm minus n, these many vectors, such that this now is a basis for W. Yeah, basis extension. This is by extension of basis idea that we have learned in our third lecture, if I'm not mistaken. Now, this is where it becomes interesting. I now want to define psi. To define psi, which is going to be a map from W to V, right? This was the idea. What have we learned just before? We have seen that in order to specify a linear map, it's enough that we specify it on the basis vectors. Yeah. Here for W, I already have a basis. What will I do? To define, I will do the following. Phi V1, I will send to V1. Phi V2, I will send to V2. And so on up to phi Vn, I will send to Vn. Yeah. What will I do with the W's? W1, I can feel wherever I feel like. It doesn't matter. W2, wherever I feel like. In particular, you can send them to 0. And so on up to Wm minus n, whatever. Doesn't matter. You define wherever, you just send them wherever you feel like. So I've defined them on this basis vector. So that means this uniquely specifies psi. This must uniquely specify psi, as we have seen before. Now the claim is that this psi is a left inverse. Why? Let's check. To check, psi is a left inverse of phi. This is if and only if psi composed with phi is equal to identity on V. Yeah, but once again, because I want them to be, I want this to be identity on V, every vector in V must be mapped to itself by this composition of psi and phi. Yeah, but see, this is also a linear map. Composition of two linear maps is a linear map. Therefore, it is enough that I show that the basis vectors, on the basis vectors, it's identity. So enough to show that psi phi acting on V1 is equal to V1, psi phi acting on V2 is equal to V2, and so on up to psi phi acting on Vn must be equal to Vn. That's what we have to do. But then this is trivial, right? Just say, notice phi Vi psi. This is the composition, the meaning of the composition, right? This is equal to phi. Oh, I don't even have to write anything. Phi Vi. Psi acts on phi Vi and sends it where? We have already specified. Phi V1 goes to V1, phi V2 goes to V2, so on up to phi Vn goes to Vn, which means psi acting on phi Vi is just Vi. Yeah. Do I have to check anything else? No, because I have to check identity on V, and V is spanned by V1 to Vn. That's it. It's true. So the fact that psi phi is identity is true for every basis vector V1 to Vn. Therefore, we are done. This is a left inverse. Now notice that I'm emphasizing on this being a left inverse, not the left inverse, because it's not unique. And you can see where that non-uniqueness is coming from. This non-uniqueness is coming from this whatever assignments. W1 up to Wm minus n can be sent anywhere we feel like. And because we have this choice, this means we have the choice in forming the left inverse also. So there is no unique left inverse, right? This is the if part. The only if part is what I leave you to prove. This goes to you as a homework, right? Okay, now similar proposition. So corollary wise for matrices, what will it mean? For matrices, it will mean that if there is a full column rank matrix, it will admit a left inverse. Yeah. So now let us go back to this other idea of right inverse that we write as another proposition. Mm, Phi once again is a map from V to W. Once again we assume finite dimensionals over F um, V W finite dimensional. Then phi admits a right inverse if and only if phi is on proof. Once again, I will do one proof, we'll do the other if part. So if it is onto, I have to show that there is a right inverse. Okay, this in fact is much easier than before. So we assume phi v to w is onto to show that there exists psi, which is a map from W to V, such that phi composed with psi is equal to identity map on W. Okay. So let W1 dot up to Wm be a basis for W. Is that all right? So because it's a basis, yeah, there's a basis for W. Because it's a basis so in order to define psi, which is a map from which is purported to be a map from W to V, define W to V, it is enough to define psi over, not over, on W1 up to Wm. So if we know how psi acts on W1 up to Wm, because it's a basis, I know it uniquely, as I have been saying again and again and again. Okay? So I have to specify this one. Now, see, phi is onto, which implies for all W1 up to Wn, there exists V1 up to Vn such that phi Vi is equal to Wi for I equal to 1 up to n, 1 up to m. Yeah, this is m, yeah. Because phi is onto, so for every W there is a V. In particular for these basis vectors W1 up to Wm, there will be V1 up to Vm. There could be multiple such V1 up to Vm. There is no uniqueness here, but there could be multiple. But there will be at least one. So I'll pick those ones. Yeah, I'll take one V1 out of many perhaps, then one V2 out of many perhaps, so on up to one Vm up to many perhaps. But then I'll take these V1 up to Vm. And then I will do the following. I will define psi of Wi to be equal to this Vi for I equal to 1 to m. That will specify psi uniquely. This specifies psi uniquely because it's a basis. It's defined on a basis. Now see what happens to phi composed with psi. What happens to this guy? So once again, in order for us to show that this is identity on W, it's enough to show that it's identity on the basis vectors. Let's check phi psi Wi. What happens to this? psi w is defined to be vi, so it's phi vi. And what is phi vi? We know that this is wi. So phi psi wi is indeed wi. This is for all I equal to 1 to n. Means it's identity on the basis vectors. So this implies phi composed with psi is identity on w1 up to wm, which implies phi psi must be identity on all of w, and that is what we wanted to show. Oh, sorry, one more part is remaining, but if part I have shown, only if part you will show. That goes to you as a homework. Okay. Yeah. Once again, you must notice that this also is not in general unique. This this right inverse not necessarily is unique. Where is that non-uniqueness coming from? You see, I have been saying that there will exist some V, right? There will exist some V1 up to Vm for these W1 up to Wm, but there could be multiple of them, out of which you're making a choice by choosing, okay, out of many such V1s, I will take this V1. Out of many V2s, I will take one V2. Because we are making this choice, we're getting one particular right inverse among perhaps many. Okay. Remember when we were defining the inverse map for a bijection, there was no choice involved, because for every W there was a unique V. That is what we had chosen for this mapping. But here I'm making a choice. That is why there could be multiple. All right. So yeah, this is it. I think this is where we close the session now. We will take this idea further, that specifying uh, linear map is enough to specify on the basis vectors. We'll take this idea further and we'll see how using the idea of coordinates, which we have learned in I think the 5th lecture, using the idea of coordinates, combining the idea of coordinates with this idea that that a linear map, in order to specify a linear map, is enough to specify it on the basis vectors. We'll combine these two ideas to see that for linear maps between finite dimensional vector spaces, yeah, such linear maps can always be represented by matrices. Okay, that we'll see in the next lecture, and still a few more stuff. But before we close, let me see whether there are any companion, whether there are any problems that I want you guys to solve. No, these are all on matrix representations, which we have not seen yet. Okay, so not required. No immediate attention or homework problems. Solve those two homework problems that I've mentioned here, and that should be okay. All right, so then all right, so I hope you enjoyed this lecture. Yeah, please post your questions, post your feedback on either YouTube or Google Classroom, or you can write directly to me on my email address. Please keep attending the live lecture, live interactive sessions also, and keep solving the problems. Okay. Once again, it goes to you always that if you face any difficulty, just feel absolutely free to contact me. Okay, or the TAs. All right, then I guess it's time to close this session. So, all right, bye bye. Take care, stay safe, stay healthy. See you.